Hi, welcome everyone. We are at module 51 of this course of the 9th week, and in this module we are going to look at fast adders. So one thing I want you to go and recollect is when we looked at the ripple carry adder, I said the carry has to propagate all the way from the LSB to the MSB in the first case, in the worst case. So this may not happen for all the input combinations that you give, but there do exist input combinations where a carry that is coming from the LSB stage may have to ripple through all the different stages and have to go to the final stage to generate the carry and sum. And if you make a wider and wider adder, this becomes a problem. So what we will do in this lecture is we will go and look at mechanisms by which we can cut down on the delay of this. So I am going to talk about one specific fast adder. So by fast I mean it is not going to be linear. The number of the delay that will be required by the circuit will not be linear in terms of the size of the addition. So if I want to do n bit addition, preferably I want something which is logarithm n based, and logarithm n is a huge reduction. So if I am going to look at, let us say, 32 bit addition, I will need 5 gate delays. If I have 64 bit addition, I will need 6 gate delays and so on. So something like that is good, because then you can make wider and wider adders. Your clock frequency will not be affected so much. So I want to talk about one specific technique here, and we will see the motivation, we will see an analogy of how to do something, and we will see how to use that in adders. So the first problem I am going to talk about, so I am not going to talk about bits to begin with, so I am going to talk about a specific problem here. So let us say I have 8 numbers, so let us say these are the 8 numbers that are given, and let us say from in software, let us say we are going to do this. I have an array of size 9, and I have numbers from location a of 8 to a of 1, which has some numbers, and let us say I have stored a of 0 to have 0. Let us say this is what I have. I have an array of 9 numbers, so location 0 to 8, and I have specific values in it. So what I want to do is, the problem definition is to find the prefix sum of 8 numbers. So this problem may seem unrelated to addition now, but I will go and connect it later. So let us say I want to find the prefix sum. So the prefix sum is defined as, what I want is, at a of 8, I want the summation of all the values from here to here, right. So all the 9 locations, I want the values stored in a of 8. For a of 7, everything from a of 7 to the right side, I want it stored in a of 7. For a of 6, everything in including a of 6 and to its right side. So I want all of that to be stored and so on. So this is called the prefix sum problem. So it's called prefix because if you are looking at the final value that is required, the sum that should be at a of I should be everything from a of 0 to a of I. So that is why it is called the prefix sum. This is the problem, and let us say I want to do this, let us say I want to solve this problem. One way to do that is start with here, take this number, add it to here, right. So that will make it a of 1 to be 1, and take a of 1, add it here, right, that will make a of 2 equal to minus 1. Then take that minus 1, add it to 3, add it to a of 3, which is also 3, that will make this 2. Then take a of 4, add the result from here, so that will make it 9, and so on. So what I am going to do is I am going to start from the right side, and if I calculate the sum so far and add it to a of I, then that will give me a of I to 0. It would end up in that result. If I do that, so then to add all these n numbers, I have to start from here, do one addition at a time, take the sum, put it in the array, take that sum and add it to the next element, find out the new sum, put it in that array location, take that new sum, add it, and so on. I will need n steps to do this. So prefix sum, if I do it in the direct way, it will require n steps. If I want to have n elements for which I want to calculate the prefix sum, then I will need an array of size, so I will have an array of size n plus 1, and I will need linear number of steps as there are elements. So the first thing I am going to do is I am going to come up with a parallel way of doing this. So I will assume that a of 0 is always going to be 0, and technically I am only interested in a of 8 to a of 1. Let us assume that a of 0 is 0 by default always, and I am going to add a of 8 should be summation of all the 8 elements, A of 7 should be the summation of 7 elements from 7 to 1 and so on. So to do this I am going to do something in parallel, and I am going to call this the recursive doubling technique. So let us see why this is called so. So the first thing I am going to do is I will assume that each element can somehow communicate with the neighboring element and can request data from the neighboring element and add it to itself. So I am going to draw an arrow to say which element is communicating with which. So let us assume that these are elements that can talk to each other. So then what I will do is I will make element A of 8 communicate with A of 7 and get the value at A of 7, whatever is stored, give it here. Simultaneously A of 7 will talk to A of 6, take the value and store it here. Simultaneously A of 6 will talk to 5 and so on. So in the first round everyone talks to their neighbor on the right side. So 8's neighbor is 7, 7's neighbor is 6 and so on. Everyone talks to the neighbor on the right side, take whatever value they have and add it to their own value, and that is going to be called the first round. So once the first round is over, then so at the first round A of 8 would have asked for A of 7, which is minus 15. Let us assume that at the end of that round 27 is added to minus 15 and that result is stored back in A of 8. Similarly minus 15 is added to 6, the result is minus 9, let us say that is stored in 7. Then 6 and minus 8, if you add up it is minus 2, let us say that is stored here and so on. At the end of first round what would happen is A of 8 will have the value stored, the value that will be stored will be the sum of A of 8 and A of 7. At 7 you will have the sum of A of 7 and A of 6. At 6 you will have the sum of A of 6 and A of 5 and so on. At A of 1 you will have the sum of A of 1 and A of 0. So what we have so far is every location has talked to the neighbor and got the values, and that is added to their current location. So clearly this is not prefix sum yet, because this is only having 8 and 7, it does not have the summation of 6 to 1 yet, this does not have summation of 5 to 1, this does not have summation of 4 to 1 and whatnot. So at the end of first round all you have is at every location you have the summation of 2 values. One interesting thing that has happened is A of 1, which is supposed to be A of 1 plus A of 0, is already attained at the end of round 1. So at the end of round 1 A of 1 is settled, you are not going to change A of 1 hereafter. So A of 1 is settled. Let us look at the next round. The next round what we are going to do is every element will communicate with elements that is 2 steps away. So let us go to the previous one. 27 minus 15 was 12, minus 15 plus 6 is 9, 6 plus minus 8 is 2 and so on, is minus 2 and so on. Let us say we have those elements there. Now every element will have to communicate with a neighbor who is 2 steps away, right. So A of 8 communicates with 6, 7 communicates with 5 and so on, 2 communicates with 0. However, A of 1 it's already settled, it should not communicate with anything. 0 is also settled, it will not communicate with anything. So let us say we do that, then at the end of it A of 8 plus A of 6 would be 12 minus 2, which is 10. However, you are not adding A of 8 and A of 6, already A of 8 had added up A of 8 and A of 7 and A of 6 had added up A of 6 and A of 5. So at the end of this step A of 8 will have the summation of A of 8, 7, 6 and 5 from the original array, then A of 7 will have A of 7, 6, 5, 4 from the original array and so on, and A of 3 will have 3, 2, 1, 0, 2 will have 2 plus 1, 0 from this side. So 2 and 1 was already there at 2, now it is also adding whatever is at A of 0, and 1 comma 0 was settled in the previous round itself and so on. So when you communicate with the neighbor of distance 2, then you get 2 more elements added up. So in the first round 2 elements were added up, in the second round 4 elements get added up, and these locations will not change anymore. A of 3, A of 2, A of 1 will not change anymore. In the second round, so in the first round 1 element got settled, in the second round 2 elements get settled, and all the other ones have addition of 4 consecutive locations. Let us do step 3. So in step 3 what would happen is every element will have to talk to the neighbor who is at a distance of 4 away. So 8 will have to talk to 4, 7 will talk to 3, 6 will talk to 2 and 5 will talk to 1 and 4 will talk to 0. And when that happens 3, 2, 1, 0 have already been settled in the previous rounds. So at the end of third round 8 will have the summation of 8 to 1, 7 will have the summation of 7 to 0, 6 will have the summation of 6 to 0 and so on. So my problem statement was add up everything up to 0, up to the location 0. So at this point in third round itself A of 7 got everything from 7 to 0 and 6 got everything from 6 to 0 and so on. So in the end of second round we had settled only 3 elements, in the third round we settled 4 more elements, so to a total of 7 elements. Finally in the fourth round every element talks to a neighbor who is a distance of 8 away. So 7 does not have a neighbor who is at a distance of 8 away, 6 does not have a neighbor of distance 8 away and so on. So A of 8 is the only one who has a neighbor of distance 8 away, which is A of 0. You add that also and at this round all the things are settled down. So what we have done is we have taken an array of size n, which is what we have to add, with A of 0 implicitly being 0, and in 4 rounds we were able to add all the 8 values and put it in A of 8. If I had done this problem with 16 elements plus 1 additional element at the end, in 4 rounds I could have done this. So in 5 rounds I could have done this. So if in general if I wanted this to be done for an array of size n, where n is some power of 2, then I would have needed logarithm of n plus 1 steps. So this prefix sum, if you do it in parallel, it can be done in logarithm n plus 1 steps. So the reason why I call this parallel is all these additions are happening in parallel. So let's go to the very first round. At the very first round you will need n adders. These n adders must take A of 8 7. So one adder will take A of 8 and A of 7, add it. Another adder will take A of 7 and A of 6, add it. Another adder will take 6 and 5 and add it and so on. In the first round you need n adders. In the second round you will need n by 2 adders. In the third round you will need n by 4 adders and so on. In the worst case, in a single step you need n adders. So we dedicated more hardware. Instead of having only one adder which takes 2 elements at a time, add it, put the result back, and then take 2 elements at a time, put it back and so on. Instead of doing that, in the first round if we put n adders, then in the next round we will need only n by 2. I can use n by 2 from the previous round and not use the other n by 2. The third round I will use n by 4 of the original n that I started with and not use the other 3n by 4 and so on. If you do all of that carefully, right, of course all of this has to be done carefully so that all the wiring is matching and so on, right. Anyway, this is now as a software program I am telling you how to do this. If you are allowed to do additions in parallel, then you can do this. The key thing is we can do this in logarithm n steps. So I am going to take this and see how to do parallel addition of binary numbers. I'll come to that in a little while. So the summary is that the prefix sum of n numbers can be done in logarithm n steps, and you can do this for any operator like minimum, maximum, add, multiply and so on, as long as the operators are associative. So instead of asking for prefix sum, I can ask for prefix min. Prefix min is at every location I want the minimum of the smallest elements from that location all the way to the right. So that is called prefix min. Prefix max is maximum of all the elements. Prefix mul is multiplication of all the elements from A of 1 all the way up to A of I for every I. So such a thing is called a semi-group operator. So let us not worry about why it is called that. It is called a semi-group operator. As long as you have such an operator, you can do prefix calculation in logarithm n steps. So you cannot do things like subtraction and so on, because subtraction A minus B minus C is not the same as A minus B minus C. So this is not for such kind of operators. So I want you to go and do a reading assignment where the last stage input at stage 0 you change it to 5, right. So I said I assume that the A of 0 is 0, instead change it to 5 and see whether you get these values, right. This is a reading assignment for you. Once you understand that, let us now look at high speed addition as we do it in a circuit. So to appreciate what this high speed addition is, let us look at n bit triple carry addition. In this case, so for some n, we start with b of 0 and a of 0. Let us assume that there is some carry in that is coming into the circuit, it produces sum and carry. Then we get b of 1, a of 1, that has to be added to carry 1, and that will produce a sum and carry and so on. So we know that the worst case, this a, b and c, a change in that may change carry 1, and that may have to ripple through all of this and may have to change c of n and s of n minus 1. We said that this requires linear number of steps in the worst case, where it is linear in the size of the width of addition itself. So let us look at a specific location j. So I am picking one of the picking one of the adder locations, let us call it j, and for a of j I want to look at what is happening to the carry, because sum is not a problem. So you give a and b, you get a sum and then you get a carry, right. The sum gets decided, but the carry has to move to the left side, it has to move to the next location. Sum does not have to move, right. Sum is decided for location j, but carry of j plus 1 has to move to the other locations greater than j. So I am interested in looking at c of j plus 1. So let us look at a of j, b of j and c of j and see what c of j plus 1 is. So this is just a truth table. If a, b, c are all zeros, c of j plus 1 is 0. If a is 0, b of j is 1 and c of j is 0, then c of j plus 1 is 0 and so on. So if I get an input carry at location j and a and b is something that I am going to give in parallel anyway, once c of j comes, I can calculate c of j plus 1, but when c of j comes, this is the truth table. This is essentially the truth table for a full adder's carry circuit, right. So the most interesting thing about this is if a and b are same, so that is the condition I have written here. If a and b are same, c of j plus 1 is actually either a or b itself. However, if a and b are not same, then c of j plus 1 is c of j. Let us go and look at this, let us validate this statement. Whenever a and b are same, so that is this row, right. Whenever a and b are same, carry of j plus 1 is the same as, so a and b are same here, so carry of j plus 1 is the same as carry of j. So in the first 2 rows and in the last 2 rows, a of j is same as b of j. You will see that c of j plus 1 is the same as a of j or b of j, you can see that here, right. However, in the middle 4 rows, this row, this row, this row and this row, a of j is not equal to b of j. In this case, c of j goes to c of j plus 1. So the way to think about that is, if I am going to add 0 and 0 in the current location, right. So in this case, a of j is equal to b of j, right. Then if I have a of j is 0 and b of j is 0, even if there is an incoming carry 1, it is not going to generate an outgoing carry. Similarly, if I have a of j is 1 and b of j is 1, if both of them are 1s, no matter what the incoming carry is, there will be an outgoing carry, right. However, only when you have this condition where where one of them is 0 and one of them is a 1, you really have to know what the incoming carry is. Once the incoming carry is known, only then you can decide the outgoing carry. You cannot settle the outgoing carry until you know the incoming carry, only under the condition where a and b are not same. So this is an interesting case, this is some interesting thing about carry. So what we are going to do is we are going to exploit that. So what we are going to do is, if a of j and b of j are 0, if both of them are 0, I do not have to know c of j at all, right. This is a very important thing. If I know a of j and b of j are both 0, I do not need to decide based on c of j. I can say that c of j plus 1 is 0 without worrying about what the incoming carry is. So I am going to make c of j plus 1 0, and the condition, I am going to call that condition as a kill condition. The kill condition happens when no matter what the carry is, it is going to kill the carry. So you look at stage j, there is some carry that is coming in called c of j. No matter what c of j is, if a of j and b of j are both 0, you are going to kill the carry. So if the incoming carry is 1, it gets killed, it becomes 0. If the incoming carry is 0, it still gets killed and the output is 0, the carry output is 0. So this is called the kill condition, A kill condition happens when both A of j and B of j are 0, because without looking at C of j, I can say that C of j plus 1 is killed or it's going to be 0. Similarly, if A of j and B of j are both 1, again without looking at C of j, I can say that I have to generate C of j plus 1 to be a 1. I have to make that carry to be a 1. I will call that the generate condition. Right. The other two conditions happens when A of j is 0 and B of j is 1, or A of j is 1 and B of j is 0. If one of these conditions happen, I need to know what C of j is, but C of j decides what C of j plus 1 is. So, let us see what happens here. Let us say A of j is 0 and B of j is 1. So, in the current stage the inputs are 0 and 1. If the incoming carry is 1, then it is supposed to be 1 plus 0 plus 1. The sum is 0 and the carry is 1. So, C of j plus 1 is 1, which is same as C of j. If the incoming carry was 0, then I have 0 plus 1 plus 0, 0 plus 1 plus 0 is sum 1 carry 0. So, C of j plus 1 is 0, which is the same as C of j itself. The same thing happens when you have A of j is 1 and B of j is 0. So, essentially what it says is, if the current conditions at the jth location, if A of j is 0 and B of j is 1 or the other way around, then I will take the carry that is coming in from the input stage, I will propagate it to the next stage. So, this is called the propagate condition. So, we have three conditions, namely kill, propagate and generate. Kill at a, so if I know that if both the inputs are the same, either we are killing the carry to the next stage or we are generating a carry for the next stage. However, if the inputs are different at a particular stage, then the incoming carry is passed on to the outgoing carry. And notice that this incoming carry being passed on to the output carry is the problem in our ripple carry adder. So, if every stage was let us say there were kills in every stage, right, then there is no carry propagation. Similarly, if there was a generate in every stage, again you can do something better. Only when you have a so you have a problem when you have this extra condition that the inputs are 0 and 1 or 1 and 0, and there is a carry that is coming in, it may have to go to the next stage. Of course, if the input carry is 0, you do not pass on anything, but it is possible that the input carry that is coming in is a 1, in which case the next stage will get a 1. This is a serious problem, and we want to see how to do this in parallel. So, let me write this as a table. So, I am going to look at condition x of j plus 1 and condition x of j. So, condition x of j plus 1 means we looked at A of j plus 1 and B of j plus 1, and based on that I generated either kill or propagate or generate. So, that is listed in the columns here. And if I go and look at the x of jth stage, again it would have taken A of j and B of j, and I would have had either a kill or a propagate or generate for that stage. Now, since j plus 1th stage is following the jth stage, I am going to look at what happens in the columns here. So, let us say the j plus 1th stage says it is a kill, which means A of j plus 1 is 0 and B of j plus 1 is 0. So, this stage is generating a kill. So, no matter what is coming from the right side, since this stage is generating a kill, it is stopping the carry from moving forward, and the carry that you have to give to the next stages is all kill. So, x of j plus 1 essentially to j plus 2th stage, which is on the left side of j plus 1, it can say that, oh, this is killing after a kill or killing after a propagate or killing after a generate. In all these cases you are killing the carry, so it is as good as kill. So, the input carry to j plus 2th stage is not 1, it is going to be 0. Similarly, if j plus 1th stage the conditions are in such a way that you have A of j plus 1 is 1 and B of j plus 1 is 1, the carry to the next stage will be a 1. So, generate, which is to the left of kill, is still a generate, generate to the left of a propagate is still a generate, generate to the left of generate is still a generate, because this is the higher order bit and this is the lower order bit. Higher order bit says, higher order bit has 1 and 1 in the inputs. So, no matter what the inputs are coming from the previous stage, the next stage to this one will have a 1. The propagate is the only place where you have to copy the stage from the previous one. So, if it is a kill, you have to propagate a kill. If it is a propagate, you have to propagate it, you do not know how to resolve it yet, and if it is a generate, you have to propagate a generate. So, propagate a kill is kill, propagate a propagate is propagate, propagate or generate is generate. And I am going to have this y of j. Y of j is all the statuses operated using this table. So this operator I am going to call star. Star is not multiplication. This is an operator called star, and y of j is x of 0 star x of 1 star x of 2 all the way up to x of j, and I assume that x of 0 is a kill, which means the very first location does not have any input, it is a kill. And what I am going to do is I will resolve this y of j, I will resolve it using this table. I will take repeated locations and resolve it. If y of j is k, then c of j is 0. If y of j is g, then c of j is 1. So at the end, if I say that if I can resolve it as a kill, then c of j is 0. At the end, if I resolve it to be a generate, then c of j is 1. Note that when you finally finish it, y of j cannot be a propagate. It cannot be a propagate, because at the end you will always have either you are propagating something that is coming from the previous side. At the end you anyway have x of 0 is k. So in the worst case it will just become, even if you have a series of propagates, at the end you have a k, so it will be a kill in that case. So let us look at carry calculation. So I am going to design a circuit called the parallel prefix circuit. I will show that in a little while, and there will be gates of this kind. So there is a module called KPG0, KPG1, KPG2, 3, 4 up to 8, and there is this stage which is kill, which is going to the parallel prefix circuit. So what we are doing here is we are giving the inputs to KPG. This KPG in turn is a generator. This will, so each stage will give its resolution to the parallel prefix circuit. So let us go and look at the inputs here. A and B are 0 and 1, so this is giving a propagate. Then A and B are 1 and 0, so this is giving a propagate. A and B are both 1 here, this is giving a generate. Then this is 1 0 here, it's giving a propagate, and so on. So what you see on the left side is what's coming in from the inputs A and B. Then the parallel prefix circuit is supposed to compute the parallel prefix. So this parallel prefix is because what we have seen here. So you look at this, y of 1 is x of 0 star x of 1, y of 2 is x of 0 star x of 1 star x of 2. You can notice that this is very much like prefix, right. So the prefix thing that we talked about when we added numbers, it is very similar to that. So for 2 I need everything from 0 to 2 operated upon. For n, everything from x of 0 to x of n must be operated upon using this operator. So since every stage I requires everything from I all the way to 0 to be operated together, this is a prefix calculation we are doing. We can construct a circuit which is a parallel prefix circuit. So I am going to show you how to do the circuit later. So we can have a parallel prefix circuit which will then resolve the prefix and give it back. So once you do that, then you can create the sum very easily. So here you have 1 and 1. If you added 1 and 1, the sum 4 here would have been 0, but it gets a generate, which means there is an incoming carry of 1, so the summation becomes 1. So let us look at each one of them. So the summation of 0 and 1 is 1, but it gave a propagate signal. The parallel prefix will return a kill. Kill means there is no incoming carry, which is a 0. So 0 plus 1 is 1, and then you add a 0, so sum naught is 1 itself. Similarly, A1 plus B1 is a 1, and it is also giving a propagate, but this is propagate after a kill, so that will be a kill. So this kill is treated as a 0, and 0 plus 1 plus 0 is 1. Here it's 1 plus 1 is actually a 0, and you are getting a kill, which means 0, so the sum is 0. So this is a stage where it's interesting, both are 1, so the summation is actually a 0, but it gives a generate signal here. The parallel prefix circuit will in turn return a generate signal. This G, when it comes to KPG, will be treated as a 1. So 1 plus 1 plus 1, the summation is 1, the carry can be ignored. There is no carry because you have already taken care of passing on the carry to the other stages. So similarly here, this 1 plus 1 is a 0, right. However, there is no incoming carry because it says the incoming carry is a kill or a 0. So which means 1 plus 1 is a 0, you do not have to add anything more and so on. I recommend that you go and give this set of inputs, add it yourself as a binary number, and ensure that the summation is correct. Let me show how the whole thing works. So, I will take a specific example. Let us say I took this example 1 0 1 0 1 1 0, I am going to add with 1 0 1 1 1 0 1. The expected sum is this. So, the only thing you have to notice is I have not taken a of 8 to a of 1, I have taken a of 7 to a of 1, assuming that a of 0 is 0. So, this is the expected result. You can verify this by directly adding. So, I have marked that as a gray area here, that is the expected result. So, I am going to do first stage, what I am going to do is I am going to generate the sums in parallel. So, 0 and 1 is 1, 1 and 0 addition is 1, 1 and 1 the addition is 0, I will ignore the carry for now. 0 and 1 addition is 1, 1 and 1 addition is 0, 0 and 0 addition is 0, 1 and 1 addition is 0. In doing this, I did not look at what is the carry that is coming from the previous stage. So, I generated all the sums in parallel, and I can also generate all the carries in parallel. So, 0 plus 1, it should generate a carry of 0, 1 plus 0 should generate a carry of 0, 1 plus 1 should generate a carry of 1, and so on. And if I go and blindly add sum and carry as it is now, so this is the sum that I generated in parallel, this is the carry that I generated in parallel. If I add both of these together, then I get this. So, now if I look at it, so when I say adding, right, I am only doing, so for example 1 is directly here, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0, and I am ignoring the carry that is coming due to this addition. Similarly, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, and this is a 1. If I leave it as it is, this is not the expected result. If you go and look at the expected result, it is 1 0 1 1 0 0 1 1. So, what I want is, I cannot do just addition of, so this addition of these two actually means it is AND of these two, right. So, the XOR of these two, so that is the sum. So, sum is XOR of, so this final result is this intermediate sum XOR this intermediate carry, but that will be incorrect, because the carry signal we have taken care of only that stage, we have not seen what is happening from the right side. This is where we need the parallel prefix circuit. We will generate the parallel prefix, so we will generate the sum in parallel, keep it aside, generate k, p or g also in parallel, do parallel prefix computation, then we will get a carry vector which we will add. I will show you the steps. So, let us say these are the numbers, these are the two numbers that I want to add. So I will calculate the sum and I will put it aside, let it be aside. Now I am going to look at only the parallel prefix stage. So 0 and 1 means it is propagate, 1 and 0 means propagate, 1 and 1 means generate, 0 and 1 means propagate, 1 1 is generate, 0 0 is kill, 1 1 is generate. I have the very first stage GPK, right. So this is before the prefix. This is the carry prefix that I wanted, this is before the prefix. What I am going to do is, I am going to make each and every element talk to the neighbor first and resolve it. So, G after a K is G, K after a K, G is K. So, generate after a propagate is generate, propagate of a generate is generate, generate of a propagate is generate, propagate a propagate is propagate, propagate a kill is kill. So, this is my round 1. At round 1, I will, so this location is settled, it will not change anymore. This is just like what we did in the parallel prefix addition, this stage is settled right now. In the next stage, what I will do is, the next step, I will take each location and communicate with the neighbor 2 away. So, generate after this generate is generate, kill after a generate is kill, generate after this generate is generate, and so on. You can notice that this is already taken care of these two locations. So, if you look at this blue line and this blue line, so this blue line has already taken care of locations this and this. This blue line has already taken care of locations this and this. So, the left foremost things will come here at this round. So, you can see the arrows and you can convince yourself that you are talking to a neighbor at a distance 2 away in the second step, and at this point this is settled, this was settled in the previous round. In this round these 2 will get settled. In the next round these 4 will get settled. So, one remark is that this is only 7 locations, it is not 8 locations. At the end of third round itself, this is over. So, now I have G, K, G, 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 K, K. I will go and interpret that as ones and zeros. So, generate means the incoming carry is a 1, kill means the incoming carry is a 0, but this is after resolving all the stages to the right side of you. Now, I can take this vector, this is 1 0 1 1 1 0, and I can XOR with the sum locations, appropriate sum locations. So, 1 0 1 1 1 0 along with sum which I can produce in parallel, right. So, I will now XOR these two, and now it is only XOR of these two, so there is no carry. This will be the final result. You can go and verify that the expected result and the correct result are the same. So, I will give you the summary of the steps now. So, you are given two binary numbers which are unsigned numbers. What you do is you calculate the sum which is just the XOR of these two bits, keep it aside, and calculate the carries. The carries are all just, so for each stage you calculate the condition whether it is a G or a P or a K. So, you can calculate this, just the location sum and all these carries simultaneously. Then you do log n steps of parallel prefix carry calculation, and that will be done in log n steps. At the end you will only have G's and K's. Take the G's and K's, interpret them as 1 and 0 respectively, that will give you a carry vector. The sum vector was available in the first step itself, and we took log n steps to get the carry vector. Take the sum vector and carry vector with appropriate shifting and XOR it together, you will get the final sum. So, all of this may look like magic, but if you follow through the steps carefully, all I have done is we have followed the same idea as in parallel prefix circuit. In log n steps we have resolved the carry condition instead of n steps that we required in the ripple carry setup. So, this is a fast adder because as n grows, your delay is not growing linear with respect to n, it is growing only logarithmic with respect to n. So, this brings me to the end of module 51. What I will suggest is you take more numbers, calculate the summation directly and keep it aside, and see whether you understand this whole process of doing parallel prefix or not. So, take different kinds of numbers so that you get different kinds of conditions and ensure that you have actually understood this whole process. So, this is a fast adder for the reason that it is able to do it in logarithm n as opposed to n. So, for n which is fairly large, so in current computers you are looking at 64-bit addition or 32-bit addition and so on, you can do this in a few gate delays as opposed to 64 gate delays. So, this is a very handy thing, and this is a circuit that you see in current day processors and whatnot. So, this circuit is called the carry look ahead adder. So, in the textbooks they write it in a slightly different way. They write the G's and P's and C's, and they have complicated equations to do the G's and P's and C's. So, here I have shown you a very logical way in which you can get your G, P and C. So, if you go back to the textbook, if you see GI, PI, CI, it is nothing more than the G, P and C, that the G, P and K that we have seen here. It is not a complicated thing, and once you know the generate and propagate and kill, you can resolve it as ones and zeros appropriately. So, this is a fairly interesting way of doing it, and this is not something that I see in undergraduate textbooks. So, it is a very useful thing to know. So, we have a fast adder, one fast adder. There are several other adders like carry save adder and so on. So, I cannot cover many of them here, but all of them in somewhere will try and break down the number of operations from n to something less than n. So, this brings me to the end of module 51. In module 52, we will see some more high speed arithmetic circuits, not adders, we will see other arithmetic circuits which are high speed circuits. Thank you, and I will see you in a little while.